In this paper, we introduce a novel level of detail system called the progressive buffer, which has been designed with modern GPU architectures in mind. Our approach stores geometry in static buffers in memory and geomorphs between different levels of detail using per-vertex weights. The approach completely eliminates any discrete LOD pops or boundary cracks while gracefully adapting to a specified frame rate or desired polygon count. The only hardware requirement is first-generation vertex shader functionality, resulting in compatibility with a wide variety of hardware platforms. Our example dataset is a 14.4 million polygon model laser scanned from real-world geometry. Here, level of detail is visualized with color coding, where red regions are at the highest LOD, followed by orange, yellow, green, and finally white. After pre-processing, our multi-resolution dataset takes up 650 megabytes on disk, yet users are able to interactively explore the model using our out-of-core rendering algorithm. In order to render extremely large datasets, we break the model into clusters, which can be loaded and rendered using an appropriate LOD. To achieve smooth LOD transitions, we geomorph from one LOD to another. If, for example, we are transitioning from the orange LOD to the lower yellow LOD, we geomorph the vertex attributes. We can then completely switch over to a lower LOD buffer. In order to allow LOD to vary across the dataset, we cannot have a constant LOD for an entire cluster. To address this, we compute the geomorphing weights per vertex using the hardware vertex shader. If the weights are based on the distance from the vertex to the camera, then boundary vertices will have the same LOD and clusters will fit together without cracks. As long as the proper buffers are used, one can render a cluster by geomorphing each vertex independently based on its distance to the camera. The distance range in which the geomorph takes place must be at least a distance r away from the LOD boundary, where r is the maximum cluster bounding radius of the mesh. In addition to straightforward optimizations such as frustum culling of clusters, we have implemented a prefetching scheme to predictively load model data and a coarse-level merging algorithm to reduce API overhead. Here we show the user interactively navigating at a high speed. The bright green clusters flashing past are clusters whose correct LOD could not be loaded into memory in time for rendering. With prefetching, the user can perform this same navigation with no missed clusters. The coarsest clusters of this model, drawn in white, are represented by a single vertex buffer and index buffer pair. The indices are laid out in a hierarchical fashion, which allows us to merge the drawing of connected coarse-level clusters, significantly reducing the number of API draw calls and consequently improving performance.